Hi everyone, welcome to the second video lecture in ECE 695, where we're going to look at GPGPU-Sim in a little bit more detail. In particular, we're going to look um, at the software design for the simulator. So the first part of the tutorial really focused on what is it modeling, what are all the pieces involved, how does it relate to what we've already talked about in class. And then this part is, well, let's take a look at the code and let's figure out where the things we talked about are in the code, how they're implemented, and how you could go and do something yourself to, implement some paper that you've read. So the whole objective of this slide set is to basically get you ready after you're done to be able to implement a new instruction if you need to. So you'll understand at least enough about how the functional model works to go in there and hack together some new instructions. If that was something that you wanted to do as part of your project. You can update the behavior of existing instructions, so you could go change the way that the multiply works if you wanted to, which would be strange because then the benchmarks wouldn't work the correct way, but you'll know where that code is and how the guts of the functional simulation actually works. And you could go fill in some unimplemented parts of the API. So as we mentioned last tutorial or last lecture, the way that the simulator works is it overrides these API calls that are coming from CUDA, and we basically implement a subset of these. Some of these we don't implement simply because there hasn't been a need in the applications that we care about. So you should know where all this code is, and then you'll have a sense of how to update the simulator so that you can add a new API call if you need it. And then probably most importantly is model the microarchitecture that you need. A lot of times you won't have to change the functional model if you're just running the standard benchmarks. You want to do something like simply change the cache replacement policy, thread block scheduling policy, warp scheduler, whatever. All you're going to need to do is change the microarchitectural model. And so you should have a sense of where all that code is after this tutorial, and a basic sense of how it's all working, so you could go in there and start hacking at it to implement whatever your idea is or whatever the paper is that you want to implement for the project. So let me give you a brief overview of the modules in the software simulator. So again, remember this is a C++ simulator that's meant to essentially emulate a GPU. And these are the sort of core pieces here. So this front part is how the simulator interfaces with the program. So it runs by, you run the simulator essentially by running the original CUDA program, but instead of taking all these OpenCL, OpenCL is also supported a very old version, so I don't recommend playing with it. But CUDA is fully supported all the way up to 10.2. So if you compile some application with CUDA, it'll essentially hijack those calls to the CUDA API, and it will go into our simulator instead of into the real hardware. And so this is really the bridge between the application and the simulation. Then it goes to this GPGPU-Sim entry point submodule, which is where we sort of capture all of these calls. So there's some code inside here where we do some management of the various APIs, and then it talks to this GPGPU-Sim entry point, which is really the beginning of the simulator. And the simulator is logically divided into three big pieces. So there is a PTX emulator. So PTX, remember, is the virtual ISA associated with NVIDIA GPUs. This thing is very well documented, so we can basically take this, it's a RISC-like ISA, and we can implement the functional model for each RISC instruction. So what does a functional model mean? It basically just means, what does an add do? Okay, you have some mnemonic for the PTX assembly instruction, add R1, add into R1 the value in R2 and R3. You have to basically code up that functionality, and that lives inside what we call the PTX emulator, because it's emulating what happens in real silicon. We're not actually running the instruction on a real GPU. We're running a bunch of C++ code that's meant to emulate what the real silicon does with that instruction. And so you can actually run the simulator, just using these pieces. Okay, just using these three pieces here without any of the timing model or any of the power model, and you can essentially get the correct functional output from your programs doing this. So if you don't really care about timing, but you don't have access to a GPU for some reason, and you wanted to just run a short, simple program to see if it's functionally correct, then you could run the simulator in what's called pure functional mode, and it will only use these three components, and it'll basically produce the correct result, but it won't generate any timing numbers. So it won't say how many cycles it took, it won't do any L1 transactions, it won't model the core, it'll just do the emulation of the instructions to give you the correct result at the end. The most interesting part of the simulator is what we call the timing model. Now, what this does is it figures out how many cycles it takes to run your program. That is the broad goal of the timing model. So much like Gem 5, it's a bunch of C++ code that's essentially meant to model the core, model the interconnect, model the DRAM, etc. And you'll essentially tick all of the modules, tick meaning simulate a clock on each of these modules, each of the various modules that make up the GPU. And on any given clock, each of those modules will have some task to do. For example, moving an instruction through the pipeline. In the beginning, you'll just have a program counter. There'll be one clock. And then you'll use, on that cycle, you'll probe the iCache to get the value of the instruction. That will happen on one tick of the simulator. On the next tick, it'll move to the decode stage. On the next tick, it'll be evaluated for issue, etc. And all of the components in the simulator work this way. So they're all essentially driven by this tick that determines what happens on this particular cycle of simulation. And this is really the most complex part of the code. And it has all kinds of additional statistics other than just cycles. So cycles is the sort of bottom line, how long did this thing take to run? But it also has statistics, since it's a simulator, you can get statistics on whatever you'd like. So simple things like number of cache accesses, cache miss rate, level of branch divergence, level of bank conflicts, memory system contention, DRAM, row buffer misses. All of these statistics are available inside this timing model because we're actually, writing C++ code to mimic what happens in the real system so we can instrument it however we like, which is really the big reason to use a simulator in the first place. Attached to it is the power model, which I'm not going to focus on in this tutorial very much. There's a paper called GPU Watch from ISCA 2013 that you can take a look at if you'd like. It's inspired by this old CPU or older CPU power model called Watch, W-A-T-T-C-H, right? Watt standing for, power, the unit for power. And so, there's this thing is basically the GPU model for that. So it was an implementation or an infrastructure effort to try and create energy numbers for a GPU, which has been validated against at least some older machines. How does it work at a very high level? It basically uses the results from the timing model. So for example, the timing model tells you how many register accesses there are, how many L1 accesses there are. And then the power model has a bunch of numbers that say that every register file access should take N joules and every L1 access should take M joules. And it essentially aggregates all these things up to figure out on any given cycle how much energy you're consuming. And there's some additional math in there because we can't perfectly model what's going on inside the GPU, especially from a power perspective. So there are some, I wouldn't call them fudge factors, but some kind of scaling coefficients in there to try and make the model match what's actually going on in a real machine. Again, I'm not too worried about this detailing this for you guys. If you are really interested in it, or your project is dependent on the output of the power model, then you should send me a message. If not, usually you can rely on timing results. And if you are wanting power for something that you're doing in your project, you don't have to go the whole way of using the GPU Watch timing model. If you just measure the activity factors that are coming out of the timing model and show that your technique reduces said activity factors, that's probably enough, because at the end of the day, that's what the power model is really doing. Okay, so the first part here is divided into a few pieces just to give you a sense of how the simulator begins operation. We'll talk a little bit about the API interface, a little bit about how the simulator starts, and then talk to you about how we actually load the PTX into the simulator, and then talk about this thing called the stream manager because it is sort of the front end to the simulator that takes all the kernel launches and then ultimately gives them to the GPU so that they can start executing them. So what is the interface to CUDA? Like I said, we override these API calls. And the reason why all of this works is that this thing called cuda-rt, which stands for CUDA runtime, is a shared object or a dynamically linked library. And when you run your executable, instead of using the normal dynamically linked library that comes with CUDA that interfaces with the real silicon GPU, you'll interface with our custom-made DLL, which is generated by the GPGPU-Sim build, and then we will implement all of those API calls where the driver would have implemented them previously. One thing to note is that modern versions of CUDA, when you compile an app, will statically link your cuda-rt shared object. So there's an option to either statically or dynamically link the cuda-rt. So if, for example, you wanted to run the code that you wrote for assignment 1 in the simulator, you would need to make sure that that executable wasn't statically linking the silicon-based shared object for the driver into the executable. And you can do that with the NVCC command argument when you're doing the the creation of the .o or the of the executable file. If you pass this -- cuda-rt space shared option, that tells the compiler, actually the linker, to not statically link cuda-rt to the executable, so that when you run the executable, it'll pick whatever shared object is in your LD library path on Linux right now. So this is critical if you're trying to run your own custom benchmarks to make sure that you include this this switch when you do the link. Okay, so how does GPGPU-Sim work in relation to a CPU? So all GPU code obviously needs a CPU because it has to do the mem copies, do the mallocs, copy things over. And the way that it works is that GPGPU-Sim doesn't have a CPU simulator. So this helps us because it makes us very, very fast. If you wanted to run a fully integrated simulator, for example, there are some open source projects that have integrated Gem 5 and an very old version of GPGPU-Sim together. It takes a very long time to run even basic applications on those frameworks because you have to simulate everything that's going on in the CPU as well as everything that's going on in the GPU. The nice thing about GPGPU-Sim is that we just run the CPU code on the CPU you're running the simulator on. So if you're running this on your laptop with a Core 2 Duo, all of the CPU code is just executing on that Core 2 Duo, and we are simply just all the GPU code is going to be running inside the simulation model. Okay, so this helps make the simulator very fast, but it's not, we don't get any detailed CPU timing information. So if you're relying on some workload that does some intimate sharing between the CPU and the GPU, GPGPU-Sim is not the right framework to use. You would want to use something more heterogeneous that has a CPU model as well. Now, that being said, there's been a number of efforts to integrate this GPGPU-Sim simulator with other types of CPU simulators. You are free to sort of take a look at that if you want, but if all you care about is stuff that's going on the GPU side, you really don't need to worry about simulating the CPU at all. So what is the interface with the CUDA API? So this is also the same thing for OpenCL, but again, don't really worry about OpenCL too much. You probably have no need to run it. But this is just essentially giving a picture of what I just said. You've got your CUDA application. It's dynamically linking to this libcuda-rt.so, which implements functions inside the CUDA runtime library. These functions are implemented inside our simulator, and then it'll talk to GPGPU-Sim through these calls to the CUDA runtime library. Yeah, and so not all of the CUDA runtime library calls are implemented. So if you are running an exotic application that has one of these calls that we haven't implemented in there, it'll die on you. And then the way to fix it is actually fairly simple. You just have to implement that particular API call. There are some API calls that have stubs but aren't implemented. Um, Whether or not that matters really depends on the application. Um, so, it's not basically it's not an industrial piece of software, right? It's not meant to replace a GPU. It's a research simulator, so not everything is implemented inside the CUDA runtime library. And this changes all the time as they update CUDA. And so as a community, the GPGPU-Sim community will implement the new runtime library API calls as needed for the applications that are important. So what is the actual interface to the CUDA API? What does it look like? So this is a code snippet from a file in the simulator, which I can just pull up here. So if you remember um, the last time we went through this, let's see. I was logged into QStruct, but it looks like my connection has failed. So let me just get back up again. Oops. Always remember to have, I think that's actually already exported, so this should be fine. Okay. So last slide set we went through this how to install GPGPU-Sim on QStruct. So I'm assuming that you've kind of already done that, or if you haven't, you have a way to do that. So all of the code for the simulator lives inside the source. So most of the code for the simulator, let me say, lives inside the source directory. Okay, so this will have the entry point. This has code for GPGPU-Sim, which is this is the timing model, and then cuda-sim, which is the functional PTX emulation code. And there's also two other directories at this top level, one called libcuda and one called libopencl. So these are the files or these are the folders where we implement the APIs that we need to override the driver DLLs. So I'm going to go into the libcuda directory because libopencl exists, but it's not especially relevant. And most of the code for this, for the for the CUDA API calls actually lives in CUDA runtime API.cc. Okay, and so this is a large file. Okay, we're talking about 7,000 lines of code that implements all of the different CUDA API interfaces that GPGPU-Sim accepts. Okay, and so I'm going to focus on one here because this is, something you have to care about because this is what ends up getting called when you do this triple bracket thing from CUDA code. Ultimately, it'll call this driver function that's called CUDA launch. Okay, and so inside this file, there will be a function called CUDA launch, which I'm showing right here. Right here. So this is the interface that's defined by the driver. And so we essentially just implement that exact same interface inside the simulator. Now, this function doesn't do anything. It just calls this internal CUDA launch function for compatibility reasons that you guys don't really have to worry about. But the guts of what happens when you launch the kernel lives inside this CUDA launch internal function. And there's a bunch of stuff happening here, like there's some debug stuff, there's some stuff to handle checkpointing that's been implemented inside the simulator that you don't necessarily have to understand if you're not really using any of those facilities. To understand what happens to actually launch the thing, I want to focus on these three particular lines of code. Okay, so the first is this G CUDA launch stack. Okay, so this piece of code right here pulls off a kernel config to basically figure out what was the last kernel that you pushed onto this gcuda launch stack. So sometime before the CUDA launch, the API will have pushed the definition of the kernel you want to launch onto this stack. So this is a global, this is a data structure that's maintained by the simulator, where another API call has said, I'm going to push this kernel onto the stack, and then eventually they call launch to say launch the last thing that was pushed onto the stack. And so what we're doing here is just pulling off this kernel config, and it contains all of the stuff that we need to launch the kernel, like the dimensions of the grid, the dimensions of each block, etc. Okay, and so that's how we get the information about what parameters you pass to this triple bracket notation. So we get that from this stack, and then we go and we get this grid by calling this init grid function. So I'm not going to get into the gory details of what happens here, but if you sort of go down a little bit further in the code and you look right here at line 948, this is where we initialize the grid with all of the stuff that we got from the from this config. So this kernel config represents the things that the API was telling us, and this kernel info t is the actual kernel state that's used inside the simulator. And there's this function that we call to populate this kernel info t with all of the relevant information the simulator needs to actually simulate that kernel. After that is done, we go down, and like I said, there's a bunch of code in here for checkpoints that you can safely ignore. And then we take that grid, okay, so this grid that we initialized right here, we take that grid and we push it onto this thing called the stream manager. So GPGPU-Sim handles concurrent CUDA streams. So we talked about the fact that you may want to launch more than one kernel at once. That functionality is implemented inside the simulator. And so as a result, we can't just call the kernel right away once we get to the end of this CUDA launch thing. We push it into the stream manager so that it can be scheduled by the stream manager, which is actually running on a separate thread. So the simulator is actually multi-threaded. So you have one thread that's running your CPU program, and then another thread that's emulating this stream scheduler. And the way that you interface with the stream scheduler is that you push stuff on to this stream manager. Okay, and so you don't end up calling all the code for GPGPU-Sim in line, like right now inside this function. Instead, you push it onto this stream manager, which will asynchronously take the kernel off of the stream and run it on the GPGPU-Sim execution thread. So that means that the CPU thread is going to keep trucking, keep going along, while the GPU simulation thread is running. And if there's any kind of synchronization, like a memcopy, as you know, is an implicit synchronization, then the CPU will wait for the GPGPU-Sim simulator to actually finish everything that it's got in the stream before the CPU can go on and do whatever it needs to do. So this is just a quick insight into how the thing starts. How does it work? How do you go from a simple CUDA program to running the simulator? This is sort of the big interface that does that, this CUDA launch thing. Okay, so let's keep going. Let me give you a few more details about what happens on startup, because I think it's probably important to gain some insight. So there's some code that actually ends up getting called before main happens. For example, there's this thing called CUDA register function and CUDA register variable. These functions get called by the API before main even starts running in the CPU program. And why do these get called? While they're inside some global constructor, some global initializer somewhere inside the program. So if you're just trying to put a breakpoint in the simulator and trying to see, well, when does main start? that's when I know when the program starts, it won't necessarily be true because these function calls are actually happening before main is even called. The first call, uh, so that means that essentially the simulator sits there unimplemented or uninitialized until we get the very first call to the CUDA API. Okay, so there's some code in there that basically waits for the first call to the CUDA API. As soon as that happens, we call this GPGPU-Sim init perf, and this will do all of the initialization steps that the simulator needs. So if there's some environment variables that store debug info that you can turn on and off inside the simulator, and there's actually a very detailed manual on what all of these do. I will provide the link to that um, in the Piazza post associated with this video lecture. It'll parse all of the option files. So there's a config file, a gpgpu-sim.config. Let me show you what that looks like for those of you who haven't taken a look at it. So this was the simulator. And so to go along with all of the source code, we have a bunch of pre-built configuration files. And so the ones that you'll want to look at are tested configs, and the one that, the two that are sort of most relevant are the SM7 Titan V and the SM7 QV100. And so you can look and you can see that this is a plain text file that basically includes all of these options that you can set inside the simulator without changing one line of C++ code. Okay, so simple things like scaling the number of SMs, right? So you can specify the number of clusters and how many cores are in each cluster. These two numbers will tell you how many SMs are in the GPU. This tells you how many memory partitions there are in this particular design. These are all the various clock domains, core clock, interconnect clock, L2, and DRAM clock, etc. All of these things can be changed without changing C++. And so that means that the simulator will read this file when it initializes, parse all of these options, and then initialize the various variables with each of these parameters inside this file. And that happens, on this initialization phase when we get the first call to the CUDA API. And all the stuff associated with the microarchitecture model, like creating the shader cores, creating the caches, all of that initialization stuff happens here once we get the first call to the CUDA API. And typically in most applications, the very first call we'll get is to this thing called CUDA register fat binary. And we use this to basically kick off the simulator and initialize all of the stuff that we need to get it up and running. So the actual code that you're going to run in simulation is PTX code, which is the virtual ISA from NVIDIA. And so we essentially need to extract this from the executable. So you run the simulator by running some CUDA binary, and then the guts of the simulator will use a special binary that's provided in the NVIDIA toolkit called CU-objdump. And what that will do is go through the binary and it'll pull out all the stuff we need from the binary. And part of what we need is the PTX itself. Now, there is an option in the simulator to run SAS, a very, very old version of SAS, which we call PTX Plus. I'm not going to focus on that too much in this tutorial. It only supports a subset of applications, and the SAS is actually quite old that's supported. There is a new simulator that we've developed that will run modern versions of this SAS, but it's not released yet, and I don't want to subject you guys to a brand new simulator in this particular class. So what we're going to focus on here is the PTX. It supports CUDA 10, compiles many different CUDA applications, and it's been around, since CUDA 4.0. We use this cuobjdump. Now, there are multiple versions of the PTX that can exist inside the executable. So essentially what NVIDIA does is every time they release a new version of the SAS, there's usually some minor update to the PTX as well. Typically, this doesn't change a lot. There's some maybe subtle differences in the number of instructions or the way the instructions are encoded. But typically, a PTX from a modern compiler looks very much like PTX from an older compiler. And so if you're compiling and you end up with a bunch of different PTX versions embedded in the executable, which if you're using the compile flow that I showed you guys earlier with the GPGPU-Sim simulations repository, we will actually embed all of the SM versions that are possible into the binary. And so the simulator will basically just take all, because it'll actually be a different assembly instruction, a different set of assembly instructions for the kernel inside the binary, and all of those will get generated. And what GPGPU-Sim will do by default is use the PTX that has the highest SM version. There's a special flag in the configuration file that can tell the simulator to not go beyond a certain SM version. And so, for example, if you've got a binary compiled with a very modern version of PTX, but you don't actually want to run that, you want to run an older version, you can cap the version that you use, and that's a configuration option. Typically, you guys really won't have to worry about that. So now we have the PTX, so we have the actual assembly for the GPU programs themselves. What do we do with it? So the first thing we have to do is parse it, because we need to figure out what all these instructions are. We essentially get a plain text PTX file that is all of the assembly instructions written out for the kernel. We need to somehow parse all of that and load it into the simulator. And the way that it's done in GPGPU-Sim is with these tools called Flex and Bison, also known, earlier versions of these were known as Lex and Yak. Which are a very well-established compiler front end, which is essentially, the thing that parses the text itself. Okay, so if you've taken a class in compilers, at the front end of all compilers is very similar. They have to take in some source code file and they have to parse it and then figure out what represent that source code in some internal way so it can actually compile it and generate the real assembly instructions for it. In GPGPU-Sim, we don't have to generate any assembly instructions. We have the assembly instructions already, but we need to parse them. So instead of parsing C++ like a normal compiler will do, GPGPU-Sim parses the assembly language to load it into the simulator so that we can use those instructions to actually run the program. And so we use these two tools, Flex and Bison, to do this. There is another parser for SAS, and like I said, it's a very old version of SAS, and what it will do is just parse the SAS instead of the PTX, and it'll internalize it into this thing we call PTX plus, which is basically just, whenever there's a one-to-one correspondence between a SAS instruction and a PTX instruction, we just translate the SAS instruction into the PTX instruction. And then there are some new instructions in SAS that don't exist in PTX, so we add a subset of those to support this PTX plus functionality. It sounds simple enough. The hard part about this is that the SAS is not documented. The SAS is the machine ISA for GPUs. So you have to reverse engineer what each of the instructions does, and that takes time and is not always super accurate. Why did we use Flex and Bison? It's very easy to update. Well, it's easy to update if you understand it. All parsers boil down to some type of state machine that sort of goes through the text and tokenizes it. And Flex and Bison are sort of a well-established way to do this. So it just made a lot of sense to not write our own parser, but just use an existing framework. You have to learn, if you actually wanted to use this, you have to learn the syntax for Flex and Bison, which is a steep learning curve. But once you've figured that out, it gives you a very flexible framework to add new instructions for PTX without changing any C++ code. So after we parse the thing and figure out what all the assembly instructions are, we have to figure out what the post-dominators are. Because unfortunately, the PTX doesn't have markers inside of it that say where the post-dominators are. And you recall from our discussion on branch divergence, you need to know where these are in order to pop the element off the stack, so that way you can reconverge the threads that have gone down different parallel paths. And so to do this, we actually perform a basic block analysis on the parsed code. So inside the simulator, there is there is basically a pass, a set like a compiler pass over the PTX that will transform it into a graph of basic blocks. And you can actually generate this graph if you're curious what the control flow graph of PTX looks like. GPGPU-Sim, if you turn on a specific option, will start spitting this out for you. The reason we have to do it all the time is because we need to know where the post-dominators are in the code when you encounter branches, so we can properly mirror the control flow divergence that happens inside the code. And so there's a bunch of code in the front of the simulator that does that pass. I'm going to briefly show you what it looks like to what we do with the lexer and the parser. So this is Flex and Bison to give you a sense of what that code looks like for if you are ever interested in how the instructions actually get internalized. If you've ever taken a compilers class, this will probably make more sense to you. If not, I don't want to belabor this, but I just want to give you a sense of where it all is. So inside the simulator, we have a ptx.l file. It stands for ptx.lax or ptx.lex. So this is the lexer file. And so the purpose of this is to essentially find tokens. So it basically, these are the tokens that are inside the code that represent each of the different mnemonics for different types of instructions. And then we have a series of commands afterwards that say what to do with that particular token. And essentially any token that exists in the code, so any string, right, that exists in the code, we need a way to interpret that and then translate it into something that the parser can understand. Because the parser, you don't want it to understand text, right? You want to basically go through and turn all of the text tokens into something the parser understands, and then pass that on to the parser that will then figure out what the broader instructions are. So any token that exists inside the PTX lives inside this ptx.l code. So these are the mnemonics for the instructions themselves. These are some special directives that exist in PTX, talking about alignment. We're defining what the registers mean. So in PTX, if you look at the code, there'll be a .u32 after a register name, for example, which tells us that this particular register is a 32-bit register, 64 is 64 bits, etc. And so if there's a new token that shows up inside the PTX, you essentially have to add it inside this .l file and then return a corresponding type here that will, give it to the parser so we can do something useful with it. And there's a default thing that happens here that if we encounter a new type, we'll print out or encounter a new token, we'll print out a warning by default, and and it'll print out the warning, and you'll just skip it. And if it doesn't make any difference in the overall execution of the program, then that's great. If it does, then you go through the warnings and find out, well, why didn't that work? So after you've tokenized everything, you go to the .yak file .y, and again, this is a special sort of domain-specific language that talks about how to actually put all of these tokens together into some kind of broader pattern. Okay, so all the tokens get turned into something through the lexing process, and then the parser comes in and then tries to group collections of tokens to figure out that this particular line was an instruction and what were all the tokens inside said instruction. Okay, so for example, right, so when we define what an instruction is, we basically say that it has to first start off with the opcode. So if you look at a bit of PTX, you can see that the opcode comes first. And there's options that there may be a left parenthesis and then some operand and a right parenthesis, and you can sort of compose what the instructions look like from the collection of tokens that we've defined from the first set of the process. So if you've ever written any kind of compiler parser, this is probably familiar to you. If this is not something that you've done before, that's fine. You don't have to understand this to use the simulator. It only really matters if you ever have to go in and implement some new PTX instruction or something. So I'm not going to belabor it here because for your projects, most of you won't have to do this. So moving on to the So now we've talked about how we got the code. So then how does the simulator actually start, and what do we do? How do we get kernels running on the thing? That's what we really care about. The simulator basically measures all of these statistics on a kernel by kernel basis. So how do we grab the kernels from the CUDA API and then actually run them inside the simulation? Now, the way that this happens is that we actually implement streams. So we talked about CUDA streams in previous lectures in this class, meaning that you can have a bunch of concurrent queues where you could potentially launch kernels from any one of those queues concurrently. Okay, so in the simple case where you're just using one stream, okay, so forget about these other queues for right now. If you're just using one single stream, you may have, a synchronization operation. So that would say that you had to wait, and then you may have a CUDA mem copy, or I'm sorry, it's going the other way. So you have a kernel launch here that gets pushed into the stream first. So you're going to run your kernel and actually compute whatever you want inside the GPU device memory. So we need to take that and actually push it into the GPGPU-Sim model. Then you want to do a CUDA mem copy and then a sync. Okay, so very sort of this CUDA mem copy is copying the data back from the GPU over to the CPU so you can read the data. Okay. Now, in this instance, the simulator is actually multi-threaded. So there's two threads operating inside GPGPU-Sim. One is the host CPU thread. So when you start running your program, that's the thread that you're running on when you get to main in the main program. And then we have another thread that is essentially going through and grabbing kernels off of one of these stream queues. Okay, so in the simple case, you have just one stream. In a more complex application where you had multiple streams, you may have, multiple things that could be scheduled to the GPU on any given cycle. And the simulation of all of the stuff that happens in the GPU happens on a separate thread. Now, the reason that we do this is because we want to allow the CPU to keep doing whatever it's doing if it's not waiting for some specific synchronization event. So for example, if the CPU code, queues up 50 kernels, there's some loop where you're just continuously calling a kernel without copying back, without synchronizing. We want it to operate in that way in the simulation as well. So if you queue up 50 kernels on the CPU, if we had it all on one thread, then we would go and try and do the first kernel in GPGPU-Sim, but we wouldn't actually get the other kernels queued up because they'd be blocked behind the kernel that you're doing right now. So in order to avoid that blocking and allow the CPU to continue asynchronously, to give us more GPU work so we could simulate something that's more like what's actually happening in the real GPU, we have a separate thread for all of the GPU simulations. Okay. And if you want to figure out what's going on here, there's a function GPU sim thread concurrent. So if you find that inside the simulator, this is some pseudocode that is sort of showing you what's happening. So essentially the GPU thread is going to wait around for a new operation to come into a stream. So that could be a CUDA mem copy or a CUDA launch. And then as soon as it's got something, it will try and operate on it. And then the actual cycle of the GPU happens inside this loop. So as long as the GPU is active, we're going to keep calling the cycle function, and that cycle function will then go and cycle all of the different elements in the GPU in a hierarchical way. And we're going to do this for as long as the GPU is active or the stream manager is empty. So we're just going to keep going through here. Now, as soon as the kernel finishes inside this loop, then we're going to print out the statistics. So if you look at the output of GPGPU-Sim, you will get a whole bunch of output every time a kernel finishes. So all of the stats, the cycles, the number of cache misses, hits, etc., that all happens every time a new kernel finishes. And so all of this is happening inside this GPGPU-Sim thread. Okay, so the CPU code is off doing whatever it's supposed to do. And then inside the GPGPU-Sim thread, we're actually doing all of this other stuff. Now, most of the time, the CPU is blazingly fast, right? Because it's running in silicon, so it's gonna queue up all of the stuff that the CPU is wanting to do, and then at some point, it's gonna want to mem copy that data back, and the CPU is just gonna stall. So in practice, what will happen in most apps is that you'll push the work onto the GPU, and it will take GPGPU-Sim hours or days to actually simulate the kernels, and that whole time, the CPU thread is just going to be waiting on the mem copy back because the mem copy is a synchronous call. Um, so it doesn't really give us accurate timing, like I said, between the CPU and the GPU, but it does give us uh, the ability to know all of the work the CPU is going to launch before it calls the next synchronize. All right, so that's the sort of broad overview. So let me talk a little bit about the functional simulator. So when I say functional simulator, I mean the thing that's going to figure out what the values are inside all of the PTX instructions. Okay, so we logically separate the simulator into the timing part, which figures out how many cycles, what all the statistics are, and the functional part that just does, what is the value in memory here? What happens when you add these two values together? All of that can be completely separated. So we could run, and we can in the simulator, you can actually run it in what's called functional simulation only, where you just simulate the PTX instructions, but you don't get any timing information. And so this can be useful if you just want to figure out what the program does, but you don't necessarily need cycle level details on simulation. So what we're going to talk about here is the functional side. So from the software perspective, what are all of the key objects inside this functional simulator? How do we simulate threads? How do we simulate instructions? And then how do we communicate values between threads? We'll talk a little bit about how the memory space is implemented, and I'll show you a little bit about the pure functional mode of the simulator. So if you look inside the functional simulator, these are the key software objects that live inside the functional sim. So all of these names correspond to structures or classes that live inside the GPGPU-Sim functional simulator. So kernel info, this basically holds all of the stuff that you need to know about the kernel itself that was launched. So its dimensions, whether or not it's finished or waiting or what have you. All the stuff that lives in the parameter memory is also contained within this object. Okay, so any parameters you pass to the kernel, for example, it all lives inside of this logical object. PTX CTA info gives you, all of the stuff that's associated with a thread block, or CTA, which stands for Cooperative Thread Array, which is basically a synonym for a thread block. So you've got information in here about the barriers that exist in the thread block. You've got the actual values that are stored in shared memory. Those also exist within this data structure. Inside of the CTA info, you've got a bunch of per thread infos. Okay, so the way that it's implemented is that each individual thread has its own set of thread ID registers, has its own private register space, program counters, call stack, and a bunch of local memory. So in theory, you could simulate the simulator as you could basically do the functional simulation as though it was a true MIMD machine, right? Because we are storing all of this per thread information in each of their own separate objects. And essentially when we do the performance timing, we will just do 32 of these threads grouped together at once. We will compute whatever we're supposed to for that particular set of threads and call that a warp. And then we've also got this collection of SIMT stacks here, which sort of sits over top of all of the groups of the thread info, because in order to figure out what the SIMT stack is, you need to know which threads are inside this particular warp. Okay, so this is like a separate grouping on top of the thread info. Inside this GPU-T, we've got all of the memory management stuff. So when we're copying stuff back and forth between the CPU memory and the GPU memory, all of that lives inside this GPGPU-T object. All of the values in global memory So, if you're copying in a 1 GB matrix and then trying to do some math with it, the 1 GB worth of matrix data lives inside this structure. Okay, the actual values for the matrix, the values for the output, all of that stuff lives inside here. Then we have a separate object that contains all of the functional info. So it tells you what is the program counter for each particular PTX instruction. So this is the sort of static value for each individual instruction once we parse the code. So we actually have to go through the code parser to fill all this stuff out. So for example, you might have an add instruction here at PC0, and then you have a multiply instruction here at PC8, and then a a load instruction here at PC10. We assume that they're all 8 bytes wide, which is what the actual SAS instructions are. Anyway, we also have a symbol table to store any symbols that are stored inside the program itself. And then all of the stuff that does the control flow analysis to figure out post-dominators, et cetera, that also lives inside this function info block. Okay. And these things collectively make up the functional simulator. So with just these structures, you can just run through functional simulation and compute the right values for the program without figuring out how many cycles we think it takes. All right. So then how do we actually simulate all of these threads functionally? So what is a thread? It's basically a program counter, a bunch of registers, and a bunch of memory locations. A CTA is a set of threads with access to the same shared memory and barrier. So that is the logical programming model for this. So if you want to look at the code for this, I don't want to go through this in a bunch of detail. But if you're curious about what's happening with the functional simulator, all of the code that actually implements the instructions is inside cuda-sim /instruction.cc. And the way that it's written, there's a one-to-one mapping between the opcode itself and the function implementation. So if you want to figure out what a mad instruction does, you can open up this instruction.cc file and just search for mad, and it'll be obvious which function is being called, and you'll essentially see that it reads 2 registers, does a multiply on them, and stores them in a third. That mapping is stored in this file that's called opcode.def. So it's basically just a table that maps together what the mnemonic is with what the name of the function is that we call, but it's typically a one-to-one mapping between whatever the mnemonic for the assembly instruction is, just to make the code easier to read. All of the threads get initialized when we launch the block. So when we actually say that this block is gonna run in the GPU, we initialize all of the stuff for the threads. Logically, we do the complete functional simulation of every instruction at the issue stage of the pipeline. Okay, so if we're talking about how we link together the functional simulator with the timing simulator, in timing simulation, you have to do fetch, decode, and then issue, right? So you figure out what the instruction is, and then it sits inside the instruction buffer, just like we've talked about before, and then eventually you decide which one of those gets issued. Once the instruction passes into the issue stage, it is for sure going to happen because it's cleared the scoreboard. We know that that it's ready to go, so all of its values are ready. And so inside the timing model, we will call this ptx exec instruction function. And this is what actually executes the instruction. And it's not done at write back, it's done at issue. And that's just a design decision because that's the first time that we know the instruction is actually going to happen. And the nice thing about doing the instruction before we actually write it back technically in the timing model is that if you wanted to do some type of Oracle stuff with the information that the instruction is producing, you can do that. Because even if it takes 50 cycles to get to the write back stage, you know what the functional output is going to be right after issue. So if you wanted to do some kind of limit study on, predicting what those values are or what have you, you can do that because you already know what the answer is going to be, even though it hasn't technically written back to the register file yet. Um, and so what happens inside this big PTX exec instruction function is it's basically a big giant switch statement, which basically says what is the opcode for this particular instruction. It reads the operands and then basically just does the instruction itself. And this is what's known as emulation, because we're not actually running this instruction on a GPU. We're not running it on a real piece of hardware. We just have a bunch of code that emulates what that particular instruction is supposed to do. And like I said, we basically look up the correct object that corresponds to a particular program counter. That's how we figure out what instruction it is that we're executing. And there's an assumption here that all of the instructions are 8 bytes, which is what real GPU instructions are anyway. They're a RISC type ISA that has a fixed 64-bit size. All right, so how do we communicate values between threads? So that's how each individual thread does its own operations. There's 2 ways. Well, there's actually more than 2 ways, but let's start with the 2 simplest ways. Global memory and shared memory, right? If you write something to global memory, another thread could potentially read it. If you write something to shared memory, another thread can potentially read it. And the way that it's done in simulation is obviously through loads and stores. Okay, so if one thread is storing something to global memory or to shared memory, then it will actually store the value at the issue stage for that particular thread. And then when another thread comes and gets issued, it could potentially load that value and it will see the updated value from the other thread. This is particularly important for shared memory because that is consistent and it is coherent, obviously, because there's actually only one shared memory location. It's not like global memory where you have different caches where the data could potentially be out of date. And so that's basically the way the simulator works for passing memory between the threads. Now, the one exception here is atomics. They're strange. So the way that we do atomics is that we do it inside the memory partition. So all the other instructions do their functional execution at issue. The atomics do their functional execution once they get to the memory partition because they do have to be ordered. Because if you're doing an atomic operation on a global value, you need to make sure that that value is actually communicated among the threads. Okay, so atomics, you can't just do it inside the core because what if there are 2 different threads that are trying to do the atomic on the same location inside the core? You may end up with, in 2 different cores, you may end up with strange results when trying to attempt to do atomics that way. So the way that we do atomics is to actually put the functional execution inside the memory partition, which means that we have to wait until that message gets to the memory partition before those atomics get functionally executed. Now, I will say that most CUDA code, especially legacy code or code that works really well, does avoid a lot of this intra-kernel communication, meaning that one thread does not typically write something to global memory that another thread then reads within the same kernel. The reason for this is that the memory ordering here is extremely relaxed, meaning that if you've taken any classes on consistency like 666 or even 565 or 437, just the basics, right? You can reorder loads and stores arbitrarily in GPUs. So there is no strict memory ordering preserved. So that means that unless you're using special instructions that do guarantee some type of memory ordering, which most programs don't do, then you have no guarantees on being able to see updated values in global memory, which is why most programs just avoid it. So if they have to share values between threads, they will usually just do this between kernels. So you'll see programs launch multiple kernels because you can guarantee that once one kernel finishes and when the next kernel starts, you will see all the results from the previous kernel if those 2 kernels are in the same stream. So if they rely on this type of ordering, then typically the programs will be composed of multiple kernel launches where the communication is assumed to be ordered in between the kernels. The memory space buffer is where all of the values are actually kept. This implements, the sort of functional uh, implementation of the main memory system. And it's essentially just a big map of memory addresses. And the way that the buffer works is that each buffer can actually contain an infinite number of pages. We have a bunch of different types of memories that are stored here. So global, texture, constant, all of those spaces share the same buffer inside the buffer memory, excuse me, space buffer implementation. The other types of memory that are not globally visible, like the shared memory and the local memory, each of these has their own buffer, and these buffers are on a per block and a per thread basis. If you're interested in how the memory is actually implemented functionally, all of this is inside the memory.h and memory.c files inside cuda-sim. Now, like I said, there is a way in GPGPU-Sim to just implement or just run it in pure functional mode. So this will make it much faster. This is great if you just want to profile the application or you want to look at prototyping some new instructions. All of the stuff you need to just do the pure functional simulation is inside this one class called functional core sim. And the way it works is it just functionally executes one thread block at a time. And it just does all the warps in round robin order. And you'll get you'll basically figure out what the right value for global memory is at the end. And that's all you really need to simulate the kernel. You don't actually need any timing information. Okay, so that's it for the functional side. Like I said, most of you may not have to touch that, but you may be curious about how it's actually doing all of that compute. The real interesting stuff is in the timing model. So let me just talk for a second about how the timing model links to this functional model. So we basically have the software is structured such that there's an interface between the functional simulator and the timing model, okay? And at the very top level, the timing model has a GPGPU-Sim object, which is essentially tied to that big GPU T that we talked about a few slides ago. Then there is a shader core object, which is tied to something called core T. And then there is the warp instruction type, which is essentially tied to the ptx instruction. So all of the stuff that you need in it, so all of the basic stuff that you need to do functional execution is stored within the functional model. And then there's a bunch of additional stuff that you need to do the timing simulation, which is what's inside of each of these respective classes. And the folder structure in GPGPU-Sim also mirrors this. So everything inside cuda-sim is in large part related to the functional model, and then everything inside GPGPU-Sim, the GPGPU-Sim folder, is largely related to the timing model. This is the picture that I've showed you, 6 or 7 times already. I'm not gonna harbor it too much, but what's important here is to understand how each of these separate components is named inside the simulator. So from slide 24 to slide 25, we'll see what the actual class names are here. Okay, so big GPU is named GPGPU-Sim. There's an object called SIMT core cluster. Inside there, we've got shader core context. Those are the classes that implement all of the stuff that goes on inside the shader cores. The interconnection network is this booksim thing. So anything that's labeled intersim is where all of that lives. And then there are a collection, all of the sort of memory, the memory partitions are implemented inside this memory partition unit class. And then there's a couple of DRAM files, DRAM.cc, that implement the whatever DRAM timing that you're trying to simulate inside GPGPU-Sim. So the top level object here is GPGPU_Sim. And this contains everything you need to do timing simulation. So what is the specific responsibilities of this class? You need to initialize everything. It's the thing that launches the kernel. It's the thing that controls the clock domain, so it knows how frequently to clock each of the given structures inside the simulator such that the clock rates work out correctly, right? So if your core is twice as fast as your interconnect, then this global structure will ensure that the core gets clocked twice for every interconnect clock. The main simulation loop lives inside here, and all of this stuff for GPGPU_Sim is implemented inside GPU-Sim.cc and .h inside the GPGPU-Sim directory. Okay, so initializing the timing model is done through this constructor. If you can go through this code, but it's sort of standard C++ code that will go through and allocate, initialize all of the different things in the microarchitecture model, also does the initialization of all the statistics, because really what you get out of a simulator is a bunch of statistics. So the whole purpose of this thing is to collect stats. So there's a bunch of code that collects a whole variety of statistics. This is called inside this GPGPU-PTX-Sim init_perf function, and this gets called at the first call to the CUDA API. There's essentially one global pointer, G the GPU, that contains this big object. And that thing gets passed around to various different places. All right, the main simulation loop, what happens here? So I talked about this a little bit earlier, but let's just enumerate it maybe a bit more specifically. So you push a kernel into the GPU launch queue, so the CPU is pushing something in, and then we basically wait for that to show up in the stream, which is the interface between the CPU thread and this GPU timing model. Once that is pushed in here, this code in red, okay, this is the thing that actually simulates a GPU cycle. You can push multiple types of operations into this stream. So you can push a mem copy, you can push a device synchronize, etc., into the stream. And whenever we push a launch into the stream, that's when we will launch a new kernel. Okay. We determine if the GPU is still active and what makes it active. If it's still running a kernel or it's still accessing memory, then we know the GPU is still doing something. So we want to keep cycling it to make sure that it can finish doing whatever it's doing. This distinction between running a kernel and accessing memory is sort of important because typically the kernel will end, or the kernel may end while there's still stores in flight. So for example, you reach the very end of the very last thread, you do your last store, and then you immediately get to the exit instruction. Technically, the kernel is done running, but there's still stores in flight. And so that's why there's this additional distinction that if it's still accessing memory, meaning we still have memory accesses in flight, the kernel isn't yet done, to make sure we actually finish off all of our stores. Then whenever the kernel actually finishes, we will print all the statistics, which is this giant dump that you'll notice from GPGPU-Sim, where you'll get all of the various things that it recorded from the GPU simulation. So at the very top level, what happens most of the time is this call to cycle. And so the first thing it does is it actually checks all the clocks. So it figures out how frequently you should clock the core, how frequently you should clock the interconnect, etc. And it only executes the ones that are ready on this particular cycle, this particular tick of the loop. And it makes sure that essentially the rate of simulation between all of the clocks is equivalent to whatever rate you provided, right? So if your core is twice as fast, you'll get 2 ticks for the core for every 1 tick of the interconnect, for example. Like I said, there's 4 domains. We said this before. One is the core, which is the sort of the SIMT clock core. It also is the clock that is responsible for issuing thread blocks. The interconnect is controlled by another clock. The DRAM, meaning the DRAM, the memory, the request scheduler inside the DRAM and the DRAM elements itself is controlled by the DRAM clock. And the L2 clock controls both the frequency of the L2 cache and, just the frequency of the L2 cache inside the memory partition. So the memory controller is controlled by the DRAM clock. All right, so how do we get to issuing stuff to clusters? So there's this one function called issue block to core. This is essentially responsible for CTA scheduling. So if you're doing something that requires CTA scheduling, you have to mess with this function. And so what it does is it looks at, what are the CTAs in a kernel that we're scheduling right now, and then it decides what SIMT core to issue those CTAs to. There's a function in here that figures out what the maximum number of CTAs you can push to any core is. And this, of course, will be based on all of those occupancy statistics that we talked about earlier. How many registers are you using? How much shared memory are you using, etc. This function will figure out, based on the composition of this kernel, what are the maximum number of CTAs that can be assigned to this core right now. Then it will go through and it'll initialize all of the threads inside those blocks. So it will, put all of the correct values in for the various registers, like the registers that define what the thread number is, etc. when you call this function. And so now the way that the thread block scheduler works is it's this hierarchical block distribution thing, which means that there's a top level, okay, and then we've talked about before that you've got a bunch of different clusters, and so each cluster will actually be composed of more than one SIMT core. So that's what this SC stands for. So in this case, we've got 3 clusters shown, and each cluster is composed of 2 cores. And the way the scheduler works by default is to try and bring as many of the clusters online as possible. So it'll round robin between the clusters first. Okay, so block 0 goes to cluster 0, block 1 goes to cluster 1, block 2 to 2. And then it wraps around. And then within the, it's this hierarchical or recursive round robining mechanism. Within the cluster, it will take the blocks that have been assigned to this cluster and then round robin those between the SIMT cores. So, the global round robin said that block 0, 3, and 6 live on cluster 0. And then essentially it'll go block 0 will live here, block 3 will live here, and block 6 will live here, and so on. And so it'll essentially try to if you don't have enough work, it'll try to bring as much of the resources online as possible, and then, backfill in a hierarchical manner. What happens inside the SIMT core cluster? This is a fairly simple class. It's just a collection of SIMT cores. What it tries to do is just call this core cycle, which will call all the guts of all of the individual SIMT cores. It is also the interface with the interconnect. So remember, we said that there's this cluster. That's what actually interfaces with the BookSim interconnect module. So when we call the interconnect cycle function, that's when the interconnect will potentially send replies back to the core cluster. So that function will essentially fill this response FIFO inside the core cluster. To sort of give you a sense of where it is in the code that each of these individual interfaces are happening, there is this interconnect, so ICNT, and it stands for interconnect inject request packet. That is what implements this interface between the interconnect and this injection port buffer. And then there's another shader memory interface that's the interface between the shader cores and that buffer. Okay, so there is this sort of level that above the individual shader cores where the accesses to the interconnect are getting buffered and aggregated, and that lives inside this SIMT core cluster class. Most of the code in the simulator lives inside the SIMT core. So that very detailed SIMT core model that we've been talking about, all of that is implemented in essentially 2 files, shader.h and shader.cc. And they implement this class that's called shader core context. It's derived from this core type that's, we talked about in the functional model, and it contains all of the microarchitectural state for the SIMT core. Now, this is the overarching core that owns all of the components, but inside of these files, there are several sort of separate classes that define each of the major components that are inside the SIMT core. So the scheduler unit is its own class. So this is the thing that will, figure out what the issue logic is for your core. There's a class that implements the scoreboard. There's a really badly named class called OpenCall-Refuti, which is basically the operand collector. There is a SIMD functional unit, so that is the thing that actually implements all of the various execution units. And then there is a class that implements the load store unit, which is essentially the memory unit, which is probably the more complex of the structures.